All right, so let's get started. Today, I want to look at the Thom isomorphism again using double complexes. And this will allow us to generalize the theorem because the Thom isomorphism, and let me recall it here, says that for an oriented or vector bundle pi from E to M, so over a manifold of finite type, integration along the fiber induces an isomorphism from the cohomology with compact vertical support of E to the cohomology of M, but you need to lower the degree by R. Okay, so I need to say that the vector bundle has rank R, and because when you integrate over the fiber, you lower the degree by the dimension of the fiber, okay? So R is the rank of E, which is the dimension of the fiber, okay? So this is the Thom isomorphism that we proved. And it assumes that the vector bundle is oriented and that the manifold is of finite type, because, to integrate along the fiber, you need the fibers to be oriented. Okay? And then we need finite type for the manifold because the technique was to use induction on the number of open sets of a good cover. Right? So today I'm going to reprove the theorem using double complexes, and that will allow us to remove the two hypotheses. Okay. Okay. Okay, so first let's look at this pre-sheaf. HQ with compact vertical support. Have I talked about this pre-sheaf before? Okay, maybe not. So a pre-sheaf associates to an open set, right? A group, okay? Let's say we have this, we have just any vector bundle. Be any vector bundle of rank R, okay, over any manifold M, and then for an open set U in M, okay, so the pre-sheaf HQ of CV associates to U the cohomology with compact vertical support of pi inverse of U. Right, so if you have a vector bundle and you have an open set U, then the inverse image is also a vector bundle. And we sometimes write it as, the vector bundle E restricted to U, right? Because a vector bundle is just a locally trivial family, yeah, locally it's a product. If it's locally a product on M, it's locally a product on any open set U. Okay? Yeah, so the cohomology with compact vertical support is defined. And this doesn't require an orientability assumption on the vector bundle or, any assumption on the manifold, okay? Well, so a pre-sheaf associates to an open set and abelian group, but you also have to define restrictions. And here there's an obvious restriction. So for every, because a pre-sheaf is a functor, so it associates to an object in open set, an abelian group, and then here the morphisms of open sets are inclusions. So if say V, is included in U, then you have a restriction map from HQCV of U to HQCV of V, and that's just the restriction map in cohomology, right? So this is the compact cohomology with compact support of E restricted to U, and you just restrict it to the cohomology with compact support of E restricted to V, okay? Because an inclusion of open sets induces an inclusion of the vector bundles, and then cohomology is contravariant, so it gives you a restriction in cohomology. So this is the restriction in cohomology. Yeah. All right. So that's a pre-sheaf. Now there's something we can. Let me see. So yeah. Okay. So but now, if you have a good cover, then there's something special that you can say about the pre-sheaf. Let me see. So oh yeah. So yeah. So suppose U is a good cover of M, and the vector bundle is oriented okay, yeah, and we look at the finite intersections of open sets in this good cover. So open of U, that's all finite intersection. Of open sets in U, okay? And so because it's a good cover, all of them are diffeomorphic to Rn. Um, all right, and so let's see. So yeah, so for an open set, that's a finite intersection in this good cover. It's diffeomorphic to Rn. So E restricted to this open set is somewhat special, right? What can you say about a vector bundle over a contractible manifold? It's trivial, okay? It's a product. So the homology with compact support, okay, of this vector bundle over the contractible open set is the same as the homology with compact vertical support of the product bundle U alpha 0 to U alpha p cross R. Let me see. Oh, yeah, so R to the R, okay? R is a rank of the vector bundle. And this, we know what this is without the Thom isomorphism, right? This was what we proved before we proved the Thom isomorphism. And what is that equal to? The cohomology of a product. The cohomology of a product bundle. It's it's called the Poincare lemma for compact vertical support. Yeah. And do you remember what this is equal to? Yeah, it's the cohomology downstairs. Okay. But you lower the degree by R. Because again, it's given by integration along the fiber. Okay. Yeah. Okay, so this is the cohomology of this is Rn, right? And the cohomology of Rn exists only in degree 0. Okay, so this is going to be when Q minus R is 0. So when Q is equal to R, you get R. And when Q is not equal to R, right, the cohomology of Rn is 0. Okay. Yes. So what this says is that on this open cover, the cohomology with compact vertical support exists only in one dimension. And this R, what is this R represented by? It's it exists in the rank of the vector bundle, but it's it's really the cohomology in degree 0 of this open set, right? And what are the elements in cohomology in degree 0? Locally constant functions, yeah. So, so this pre-sheaf, yeah, this is HQ with compact vertical support of U alpha 0 to alpha P, okay? This pre-sheaf on the open cover is precisely the locally constant functions on that open set, okay? Yeah, so these are the locally constant functions on this open set. Okay? And that's a pre-sheaf too. Okay. So what have we proven? Yeah, so what we have proven is that on a good cover, U of M, this pre-sheaf is equal to it's equal to the pre-sheaf of locally constant functions on the open set. So it is equal to R bar. Okay, it's the pre-sheaf of locally constant functions. Yeah. All right. Yeah. Okay. Okay. So now we understand this pre-sheaf. Okay. And for compact support, we had a Maya-Vittora sequence for two open sets. But, you know, again, you can generalize it to infinitely many open sets. Okay. So let's just write that down. All right, so I need, what do I need? I need an open cover, right? So, yeah, so this is the Maya-Vittora sequence for compact vertical support. This is on any manifold. So theorem. Yeah, so let you be an open cover of a manifold of the manifold M. And this is always indexed by a linearly ordered set A and pi, a vector bundle of rank R. And the Maya-Vittora sequence, okay, starts with, it starts with formed with compact support on E, and then it goes to, you restrict it to open sets. And then it goes to the differences, pairwise differences. And so on. Okay, so you have the first map is just restriction, and then the other maps are delta, the alternating differences. Okay. Is this defined by the same formula as before? And the theorem is that this is exact. Okay, so then now notice that this sequence goes forward. Okay? Let me see. Yeah. Oh. Yeah, this sequence, like it goes in the same way, you know, as the Maya-Vittoria sequence for just forms on an open set. Okay? When you have compact support, it will go the other way. But here, the compact support is only in the vertical direction. Okay, so the sequence goes in the same way as the Maya-Vittoria sequence, you know, with general support. Okay, and the proof is the same. It's exactly the same proof. I mean, right. So, right, you show that del square is 0. I mean, it's the same del as before. And then you find the homotopy K, you know, going backwards. So it's the same proof as for the Maya-Vittoria sequence for just forms. Okay, exactly the same proof. All right, so we have this Maya-Vittoria sequence with compact vertical support. And okay, so now let me introduce a check de Rham complex for vertical support. Oh yeah. Oh, I'm sorry. Gosh, yeah. Okay, thank you so much. I really appreciate that. Right, E restricted to U alpha 0, okay? And here it should be E restricted to U alpha 0, alpha 1. Yeah, I don't want that mistake to be filmed and live forever. Yes, every time you see a mistake, please point it out to me. Okay. So let's see. Let's write down this. Check the Rham complex for compact vertical support. Okay. Well, so it's the same hypothesis as in the Maya-Vittoria sequence. And here you have an open cover of the base manifold, but you can take its inverse image, right? So I inverse of U, let this be the a collection of all inverse images of open sets in U. And the inverse image of an open set is open, so this will be an open cover upstairs. This is an open cover of E. And yeah, and so now I will define my check-the-lam complex definition. So it will be CP U, not U, but pi inverse of U, because it's upstairs. And then HQ of CV, okay? So what is this? CP means that you take, you know, the P plus 1 fold intersections. So you look at pi inverse of U of alpha 0 to alpha P, and then HQ associates to this open set the Qth cohomology with compact support. And then alpha 0 is less than alpha P. Okay? So this is the definition of the check-the-lam complex with compact vertical support. Okay? Yeah, so let's draw this complex. Let me see. I probably should put that down there. Oh, yeah. So I will call this is a double complex. I'll call this KPQ. Okay? KPQ. Okay, so here you have, say, C, no, you have the direct product of omega. Oh, no, gosh, God, no, sorry, no. Yeah, no, in the check-the-lam complex, we don't start with cohomology. No, we start with differential forms. So this should be omega Q CV. Okay, omega Q CV. Okay. Okay. Yeah. Okay. So we have omega Q pi inverse U alpha 0 to alpha P there. And then that goes to omega Q pi inverse of U alpha 0 to alpha P plus 1. Here is the difference map. And down here, you have omega Q minus 1 pi inverse of U alpha 0 to alpha P. Okay, so this is the double complex K. Um, now, can you tell me what is H delta? Because delta is a differential, right? Delta squared is 0. So you can take its cohomology, H delta. Yeah. Let's see. The first one here is in the 0th column, it's the direct product of all Q form. Oh, sorry, this should be forms with compact vertical support. Did I put that down there? Yes, I did. Right. What do you know about the rows? Is it completely exact? Is it exactly the same as the Maya-Vittora sequence? Yeah, it's just missing this term, right? So the rows, they are simply the Maya-Vittora sequence for compact support, except it's missing this term, okay? Now this term is the kernel of this delta, okay, because the sequence is exact, okay? So yeah, this double complex, the rows are exact, except for the 0th term, okay? When you take H delta, so you need to take the kernel of this map over the image, but there's nothing before, right? So, so when you take H delta, because the sequence is exact everywhere, except for the 0th column. And in the 0th column, you need the kernel of the first delta. And the kernel of the first delta, according to the Maya-Vittora sequence for compact support, is omega q with compact support of E. It's the global form. So when you take H delta, this is what you get. This is the picture of H delta. Mhm. Okay. And now if that's H delta, what is H dH delta? Okay, so when you take HD, right, now you're taking the cohomology in the vertical direction. So what do you get? You take the cohomology, you'll have non-zero elements only in the 0th column. This is the 0th column. And what is the 0th column? When you take HD of H delta. Yeah, yes, very good. It's the cohomology with compact vertical support of E. okay? That's the first column, okay? Now, last time we proved a tic-tac-toe lemma that says if H delta has only one non-zero column, then what is the conclusion? If H delta has only one non-zero column, then the tic-tac-toe lemma says it says HDH delta is isomorphic to, yeah, it's the cohomology of the single complex associated to the double complex with this differential big D, right? Okay, so that's what we can say. Yeah, thus. So by the tic-tac-toe lemma, so since H delta has only one non-zero column, H delta is isomorphic to H big D of the double complex, which is, yes, over there, which is C star of pi inverse U omega star with compact vertical support. Okay. Okay, very good. And now let's do it the other way. Now, if we do it the other way, that means we calculate HD first. So we're going in the vertical direction. And so you have this open set. And you have the exterior derivative D with a sign, but the sign doesn't matter. Anyway, you have this exterior derivative D going vertically, okay? Yeah, so what is, yeah, if you go vertically, yeah. If you go vertically, you just get cohomology with compact vertical support in every box. Yes, but that's that means every box could be non-zero, right? And so so we should use a good cover. Okay, yeah. So let's go vertically, but we use a good cover. So let me do it over here. Okay. Yeah. Okay. So let U be a good cover of M. Yeah. And for an open set that's a finite intersection this could cover. You know that pi inverse, well, that's E restricted to this open set. And because the open set is diffeomorphic to Rn, this is a product. Oh yeah, we did this earlier. So if you take the cohomology with compact support, vertical support, sorry, this is U alpha 0 to alpha p cross R to the R. And this is HQ minus R of U. So that's by the Poincare lemma. And then this is R for Q equal to R and 0 for Q not equal to R. Gosh, I wish I didn't erase that earlier. Anyway, we had this before, okay? And so you see that everything will be 0 except when Q is R, okay? So if you take HD, you get only one non-zero row, okay? That's when Q is equal to R. Yeah, when Q is equal to R, let me see. So, yeah, you just get R, but it represents this, right? Yeah. So let me see. Oh. It should be a product. Yeah. This is just on one open set. Yeah. Yeah. So we should have you know, the product. So what do we have? Let me see. So what we have, yeah. Now this is going to be C0 of, okay. Okay, let me just, let me write it down this way. So it's a product of HR with compact vertical support of U alpha 0, right? Yes. When you take D, then you just get cohomology. So the general term is HR with compact vertical support of U alpha 0 to alpha P. And everything else is 0. Okay. That's HD. HD. And you know that each of these groups is R, right? Okay. So let's rewrite that. Sorry, again. Just a minute. Yeah, just a minute here. I always forget to put in the pi inverse. There should be pi inverse u alpha 0 here. And you should have pi inverse here. And this should have pi inverse. Okay, yeah. Okay, so what is this? In a typical box, this is what you have. Now, oh, gosh, I forgot the H here. um, well, so this is the pre-sheaf on the open set U. Okay. So this is, well, these are the Pico chains of the open cover U, and then with values in the pre-sheaf H, R of CV, right? That's precisely what that is. To every open set, okay, that's a finite intersection of open sets in the good cover, you associate, you know, this cohomology group. So it's that. Okay? Yeah. So HD has only one non-zero row, and that non-zero row you can write as this chain group. Okay? In the rth row, so you have CP of U, HRCV, going to CP of U, CP plus 1 of U, HRCV. Okay? Now you notice that now you're using the open cover on the base. Okay? Where here you're in the original double complex, you're using the open cover on E, upstairs. Okay? But here it's downstairs because this pre-sheaf associates an open set downstairs with the cohomology of its inverse image. Okay, okay, so this is what you have. And what happens if you take H delta of HD? Okay. Obviously, it's going to be 0 everywhere, except in the rth row. And what do you get in the rth row? Well, I think maybe I'll let you think about it over the break. Okay, so let's take a break for 10 minutes and you tell me what you get. after the break. Okay. Okay, so I want to remind you, if I make a typo on the blackboard, yeah, please let me know, tell me. And if my posture is bad, let me know too, say, straighten up, professor, yeah. Um, so, yeah, now here we have the co-chains on an open cover, with values in a pre-sheaf, okay? And we have this differential delta. So if you take delta of, this differential complex, what do you get? What do you get? You get the check cohomology of the open cover. So we get a single row, and it's the check cohomology of the open cover with values in the pre-sheaf HRCV. Hmm? Okay, that's H delta HD. Now, we have a tic-tac-toe lemma that says that if HD has a single non-zero row, then H delta HD is isomorphic to what? So let me see, where do I write that? Yeah, so let me write it here. So since HD has a single non-zero row, by the tic-tac-toe lemma, HD, so that's of the original complex K is isomorphic to H big D of K, and K is let me see, where is K? I think I have erased it. K was the original complex. It's C star pi inverse U with omega star CV, right? That was K. Okay, yeah. Okay, so if you have a good cover, then you have this isomorphism, and then for any cover, we have another isomorphism. Sorry, just a minute. Sorry, just a minute. No, it should be H delta HK, right? Yeah, if HD has only one non-zero row, then by the tic-tac-toe lemma, H delta HD is H big D. And earlier, when we had a single non-zero column, we get, yeah. That I erased when we had a single non-zero column. So earlier, um, Yeah, this is for a good cover. Earlier, we didn't have any hypothesis. So for any cover, we had HD, H delta is isomorphic to HD. So that means for a good cover, you can compute H big D two ways. Okay? Oh, I'm sorry. Let me see. Let me just a minute. Turn this off. Okay. Yeah. Okay. So let's write down our conclusion. Okay. I need to keep this. Now, our conclusion, yeah, earlier, we had a single non-zero row. H delta gives us the global form through compact vertical support. Then we take HD. So this was cohomology with compact vertical support of E. Okay? And this, yes, H delta HD is over here. It's the check cohomology of the open cover. Check cohomology with compact vertical support. Just a minute. Check cohomology. Oh yeah, check cohomology of the open cover with coefficients in HR of CV. From here. Okay. And so for a good cover, we get an isomorphism between cohomology with compact vertical support and check cohomology. Okay? And that's the Thom isomorphism theorem. So notice that we haven't assumed that E is orientable. Okay, so we get this Thom isomorphism because Thom isomorphism calculates the cohomology with compact vertical support of a vector bundle. Yeah. So thus, oh, it's not quite Thom isomorphism yet, because now we still have an open cover, right? The Thom isomorphism should give you cohomology with compact vertical support of the vector bundle, and relate that to the cohomology of the base. But right now, we don't have the cohomology of the base. We have the cohomology of an open cover. So what we get is this. For any vector bundle over M, and U, a good cover of M, the cohomology with compact vertical support of E is isomorphic to the check cohomology of the open cover with coefficients in this pre-sheaf. Okay, now the degree should correspond. So let's say we want Q here. Now Q, let me see. So H delta, right? H delta has only one non-zero column, right? So HD is going to be, in the 0th column, and then Q, okay? Right? when you have a double complex, the cohomology has 2 degrees. In each box, you have 2 degrees. And so it's H big D of 0 Q. But no, just a minute. Yeah. No, just forget about this. Let me see. So, H. Okay, no, maybe I'm going to, okay, just forget about the degree here. I have this isomorphism, and this one, let's see, HD has 1 non-zero row. Yeah, so this one comes from this picture. Okay, and this is in, oh, no, this one. Sorry, yeah. This one comes from this picture, right? Yeah. That's when you have only one non-zero column. This one comes from this picture. Okay. And now I want degree Q. Okay, now degree Q here should correspond to degree Q here. But here, I'm already in the rth row. So to get total degree Q, it has to come from the box that's, which box should it come from? Yeah. So that the total degree agrees. I mean, it doesn't come from this box because in this box has degree R. Okay, this box has degree Q. So yeah, degree Q here should correspond to the total degree Q here. Total degree Q here should correspond to total degree Q here. So this box doesn't correspond to this box. Which box does it correspond to? Q minus R. Yeah, it has to come from P is Q minus R. Okay. So that the total degree corresponds. Okay? So this is what we have. For any good cover. But this side doesn't depend on the good cover. So what this statement says is that for any good cover, the check cohomology with this pre-sheaf as coefficient are all isomorphic. It's constant, okay? Yeah. So thus, for any good cover, U of M the Chick cohomology is constant. It's all isomorphic to HQ/CV of E. So this is constant in U. Therefore, when you take the direct limit over all good covers, you get the same thing because it's constant. You just, when you take the direct limit, it's the same, right? It stays the same. And when you take the direct limit over good covers, because the good covers are cofinal, it's going to give you the Check cohomology of the topological space. And here the topological space is M. Okay. The definition of Check cohomology is that it's the direct limit over all open covers. But because good covers are cofinal, you can use good covers to calculate Check cohomology. Right? We showed that earlier. So because good covers are cofinal. In all open covers of M. Okay. Yeah, and this is the Thom isomorphism. Okay? It tells you that the cohomology with compact vertical support is the cohomology of the base, but with coefficients in a pre-sheaf. Okay? So we have proven the Thom isomorphism theorem. And this is for any vector bundle. Over any manifold the homology with compact vertical support of E is isomorphic to the cohomology of the base, the Check cohomology of the base, but with coefficients in this pre-sheaf. Okay? And you notice that E doesn't need to be orientable and M doesn't need to have finite type. Okay, so no, E need not be oriented and M need not have finite type. Okay, but if E is oriented, then we know what this pre-sheaf is. So so if E is an oriented vector bundle over any manifold, then we know that if E is oriented, this HRCV is just the free sheaf or locally constant functions are. So, or then this theorem says, okay, HQ CV of E, okay, yeah, it's isomorphic to, just a minute. So this is isomorphic to the check cohomology of U in degree Q minus R of M with coefficient in that, then, but we know that when E is oriented, this pre-sheaf is isomorphic to the pre-sheaf of locally constant functions. So it's this check cohomology, right? You can replace the pre-sheaf by the pre-sheaf of locally constant functions, but we have the check-de-Rham isomorphism that says that the check cohomology of a topological space is isomorphic to de Rham cohomology. So this is the check de Rham isomorphism. Okay. So when E is oriented, we end up with this statement. And this is exactly the same statement as the Thom isomorphism that we proved earlier. Exactly the same statement, except what is different here. Except, yeah, except M is not assumed to be a finite type, okay? So this is the same statement as the earlier Thom isomorphism theorem, except now M need not be of finite type. Okay? Yeah. So we have managed to remove that finite type assumption from the Thom isomorphism theorem, okay, using double complexes. Now, we can also use this technique of double complexes to generalize Poincare duality. Okay? Because earlier, we proved Poincare duality under the hypothesis that the manifold is orientable. Okay? Then you have an isomorphism between cohomology and cohomology with compact support. Now, using double complexes, you can prove Poincare duality without the assumption of orientability on the manifold. Okay? But you have to replace, one of the cohomology groups with check cohomology. Yeah, but I won't do that. So next time, starting next time, what we are going to do is we're going to generalize the technique of double complexes. Okay, so right now we go only 2 steps, right? We start with a double complex. We calculate HD, then we calculate H delta. Okay. What we are going to do, okay, and then if it so happens that HD has only one non-zero row or one non-zero column, then we have some theorems, but in general, HD or H delta will not have just one non-zero row or non-zero column. And so this new technique is a generalization called spectral sequences. So after you get H dH delta, then there's a third differential, D3, and you can calculate D3 of H delta HD, and then D4 of this cohomology, that has 3 steps, and you can keep on doing that. You can calculate the cohomology forever, and the theorem is that if you start with first quadrant double complex, it's going to terminate at some point, okay? Maybe not after 2 steps, but after finitely many steps. And then that will be the cohomology of H big D, okay? Yeah, so starting next time, we'll be doing spectral sequences. And it gives you a technique that can allow you to calculate a lot more cohomology groups. And so, for example, in the homework, there is a problem on the complex projective space. And when you calculate, like, one step, you will get a picture like this. So you don't have a single non-zero row, you don't have a single non-zero column. Okay? But with spectral sequences, you can calculate further, and that will give you the cohomology of the complex projective space. Now, without spectral sequences, because this is a relatively simple picture, you can use the same technique that we have been using, for double complexes to prove the theorem that, this, I forget if this is HD or H delta, but, it's one of them. And if it's HD, then if HD looks like that, then you can prove that H delta HD is also H big D, and it's also H dH delta, and that would allow you to calculate the cohomology of the complex projective line CP1, without spectral sequences. It's a very elementary case of spectral sequences, but you can use double complexes to deal with this situation also. Okay, so this concludes chapter 2. And then spectral sequences is a new chapter, chapter 3, okay? And we will end the course with this chapter, spectral sequences.